Hi, I'm Hyun from KAIST. I'll present differentiable appearance acquisition from a flash-no-flash RGB-D pair. This work is a collaborative work with Hyunho, Juho Lee, Dahyun Kang, James Tompkin, and Min H. Kim. Rendering is a process to generate 2D images from 3D models. It requires 3D geometry, reflectance map, lighting conditions, camera parameters. Inverse rendering is the opposite procedure. Given 2D images, obtain information needed for rendering. Appearance acquisition is needed in this step to contain reflectance information. Through inverse rendering, we can reconstruct objects in real world, and we can play with the objects with realistic appearance. There are previous works that try to reconstruct intrinsic properties of objects from a few shots of RGB-D images. Baron et al. And Kao et al. Take this approach. They estimate intrinsic property of objects successfully, but reflectance is limited to diffuse albedo only. There are also deep learning-based approaches. Sang et al. And Bose et al. Use thousands of rendered images, including geometry and reflectance, to train deep learning network to obtain SVBRDF. These approaches are fast, but the model is easily overfitted to the trained data, which makes it hard to adapt to various real-world objects. For input, we use an RGB image pair with and without a flashlight and a depth map. Our method estimates diffuse albedo, specular albedo, surface roughness, and refined normal and depth. These input images can be obtained with a DSLR camera and a depth sensor, or just with a conventional mobile phone. Now, I'll give you an overview of our method. First, from the coarse depth map, we compute initial normals. From flash and no-flash image, we compute flash-only image while assuming flashlight as a point light source. And from no flash image, we cluster colors for material segments. The optimization is done in two steps. First, we estimate environment illumination, assuming no flash image is taken under diffuse ambient light. Then, under this illumination, we jointly optimize SVBRDF and geometry-related parameters. We first obtain a flash-only image by subtracting the ambient-only image from the flashlight image. We mainly use flash-only image for the joint optimization, since we assume that there's only one point light source. We can simply formulate the flash-only image as the multiplication of shading and BRDF. Here, we use the Cook-Torrance model for BRDF, which is summation of diffuse and specular reflection terms. Let's look at the detail of the optimization part. In step 1, we estimate environment illumination in order to obtain diffuse albedo Q from no flash image. By assuming no flash image is taken under diffuse illumination, we can parameterize the illumination G as 9 coefficients of the second-order spherical harmonics basis function. Once G is optimized, we can compute diffuse albedo as well. Later, this diffuse albedo is used to register the diffuse albedo obtained from flash-only image. In step 2, the joint optimization is done in coarse-to-fine manner, and there are 5 optimization parameters being used. To obtain refined geometry, we use depth difference matrix and relative rotation matrix. To obtain SVBRDF, we use per pixel diffuse albedo and specular albedo and roughness per material cluster. Let's look at the objective function in more detail. Our objective function consists of 3 photometric terms and 3 geometric terms. The first term is photometric consistency term. This term reduces the difference between input flash-only image and rendered image in foreground pixels. Second term is diffuse albedo constraint. This constraint reduces difference between optimization target diffuse albedo and diffuse albedo from no flash image, which is computed from step 1. In our ablation study, we found that bright pixels due to specular reflection is harder removed without this diffuse albedo term. Please refer to the detail of the additional constraints in the paper. We compared our method with Baron et al. Using synthetic data. For input flash-only image and depth map, since Baron et al. Estimates reflectance up to diffuse albedo, the optimized diffuse albedo contains specular reflection, while ours successfully removes specular components. We evaluated on synthetic data and compared with Kang et al. And Bose et al. As well. Both use deep learned priors, whereas we forego this and use additional sensor depth information. Results show that ours show less error compared to GT. Note that since it's unfair to directly compare the methods that do not use depth for inference, we added random noise to the ideal synthetic depth. We also compared results of real-world objects. Considering deep learning methods use lots of priors for each parameters, results of Kang et al. In the first row show inconsistent geometry. Results of Bose et al. In the second row show unstable SVBRDF results. Results of our method in the last row show that additional depth map helps estimate both geometry and SVBRDF more robustly. For chicken object, results of Kang et al. Show flat normal and inconsistent depth map. For Santa object, results of Kang et al. Again show flat normals and inconsistent depth, and Bose et al. Estimates head as gold-like material. This slide shows relighting results of Kang et al., Bose et al., and ours. Of course, our method is not free from limitations. Since we assume the material surfaces are dielectric, specular albedo is estimated as only monochromatic and has the same color as the illumination. Second, for the saturated flash image, optimized diffuse albedo and normals show degraded performance. More discussions can be found in the paper. In conclusion, by using easily accessible devices like a smartphone, we reconstruct both geometry and SVBRDF from a single view of a RGB-D pair images with and without a flashlight. Thank you for listening.